So, what are we doing now then to it?
What we're doing now is we're doing exactly the same experiment again. So all of these are that single line that we saw for the non-polarized pulse. Except what's happening now is that the length of the radio frequency pulse that you send into the sample has changed. So what we're trying to do is adjust that length for future experiments such that we get the maximum amount of signal.
Okay.
So you see that this is a sine wave.
Yeah.
So basically we want the top of the sine wave, and it will keep going forever. So if you have a pulse length where the maximum's at 5 microseconds, there'll also be another maximum at 10, that is slightly lower, so you can set it to all these maximums. So as long as you set it somewhere there, it means you'll get decent signal.
Yeah.
For these samples, it doesn't really matter so much, but for other stuff, it can make a hell of a difference. Okay. So then, click save. And then click the evaluation dialog button, which is this 1-2 button here. Somebody's drawn a picture. And then to analyze this, you use WAM, which is taking the data in the window and getting the absolute magnitude. And then that'll give you this. You click on the peak, you'll see that X says 5. It says 5 seconds. The software is wrong. It's 5 microseconds.
Right.
And then what you do...
So we're just estimating the peak then, are we not finding it out?
No, as long as you're about there, it's fine.
Okay.
Even if you set it here, you still work. If you set it down here, it would look like crap.
Yeah.
So then what you do... So what it says is that you should change this. So you should go into acquisition parameters, then configuration, and you should change this number to the maximum here. You'll see this grayed out at the moment, and it's always grayed out after an experiment finishes, and so you can only edit this value when you set up a new experiment.
Right.
So you set up a new experiment first. So the new experiment is called NPS, and so this is like MP, except that we do it over a number of different waiting times, basically, to find out what the signal is. I'm going to turn this down. It's really hot. Okay. So at the moment, we're assuming that our maximum T1 is 0.2.
Yep.
So it's at 0.2 there. We're going to do this at 7 megahertz, and we're going to go to that, go to conf, acquisition parameters conf, and then change this guy to the maximum here, so which was about 5. If it's between 4.5 and 5, that's okay. If it's anything different than that, something is definitely wrong.
That's for all samples?
If you left that at 5 for all samples, you wouldn't see any problem at all. But it's up to you whether you want to go through it or not. Don't do it, it's not worth it. So let's start this experiment now. So now what we're doing is we are doing a bunch of different acquisitions, again the same as the MP pulse or the same as the angle pulse, except what we're changing now is the time that we wait between acquisitions. So each one of these is sending in a pulse, waiting some time, and then acquiring a signal. And so what we'll do now, because I told the machine that we think our maximum T1 is 0.2 seconds, and that our recycle delay should be a second, it's actually way too long. So what we should see, I guess you guys have seen this from your research already. But, so you should get a graph that's like intensity versus some waiting time that either looks like that or that.
Right.
Where you get a bunch of different points, and then so this would be I equals I naught e to the minus t over tau, where tau is equal to t1. Yeah. So you can see that if you set, so the way the machine works out which points to do is by taking a first value of 4 times whatever your T1 max is, to 0.01 times whatever T1 max is, and it does logarithmically, 16 logarithmically spaced points between that, or linearly spaced. So you can see if you set that too long, what it will do is it'll have 16 points that are all in this bit here, in the flat region. So if we analyse this, so that's done. Click save. Got evaluation dialog, and now we want RAM to get the relaxation rate using WAM. It's basically just use those two.
Yeah.
And you see that? So what we're doing is we're sampling this flat bit, or well, this flat bit, loads, and that won't give you the best data. So what you want to do is sample the whole exponential curve. Okay, so we've got some value of T1, so we can send that back to our parameters. So if you click correct T1 max, what that does, it takes this value here that's just worked out and bungs it in there instead.
Yeah.
So do that, got bung in there, and now we can change the recycle delay to 5 times that instead, which would be 0.2 seconds. So now this thing's 5 times faster already. So if we run the same experiment,
Would you do 0.2 or 0.25? As long as it's about roughly, yeah.
I definitely do more than 2 times, but it doesn't matter. The 5 times is a bit of a...
Just a little, yeah.
It's to make sure that it's enough time, but it doesn't need to be fast. So if I do this again, okay, beautiful. So now we're sampling the whole curve, and that's what you want.
Okay.
And so once you've done this for one sample, you can use a T1 of whatever 0.04 as your starting guess for your next sample at 30 degrees, and they should be similar enough that you can then use that to tune, and then you don't have to wait as long as we did the first time setup, so the whole thing goes a lot faster. Okay, so what we've done so far, we have set up the observe offset, we've set up the length of the pulse, and we've measured T1 at 7 megahertz. What you want to do is generate a bunch of relaxation dispersions. So R1, which is 1 over T1 versus frequency, curves like this, as a function of temperature. So what we've done so far is just get 1 point on this graph. So the next thing you do, now that this is set up okay, is go to Actions, Profile Wizard. This is the wizard. And then you synchronize this wizard with the acquisition parameters that you just set up. So you click synchronize, that puts T1 max in there, etc. And then what we're going to do now is do exactly the same experiment, but for 20 frequency points between 10 megahertz and 10 kilohertz. So the rest of this is fine. And then what you want to do is save the data file, so you click change on one of those, and then just input the file you had there before. Populate that, everything else is fine, so then click execute. So now it will start doing the experiment at 10 megahertz. Okay, and then it will say, out of tolerance. Okay. The recommended action is try again, so we must try again.
Yeah, let's try
the recommended action. As with most machines in physics, the machines themselves are top of the range, best in class. The software is awful all the time. The discrepancy is small. Recommended action, go on. We will go on. Yes. The error of this one scan measurement was 0.3. If the error is not above 1%, then you only need to do one scan. All of these should have an error of less than 1%. If not, they say they recommend to use multiples of 4. It's recommended. Recommend. Yeah. This doesn't make sense. And to use multiples of 4, you don't have to. I would just use 1 the whole time. So you can say yes. So now what's happening is it's measuring across this frequency range, and then it will get 20 points between 10 and 10 kilohertz.
Yeah, when did we tell it what frequency to do it?
It's set up automatically in the profile wizard to go.
Oh, so does it itself? Okay.
Yeah, so you can set up the number of points. You can set up the range as well. I'll show you, after this is run, I'll show you where you can change those things in case you want to.
So these are just the parameters it's finding out?
Yeah. So that's the frequency that's running in megahertz.
Oh,
the T1 value, the R1 value, which is just 1 over that, and then the error. And then there's an absolute error as well.
How come there's a signal for 0 frequency? How's that?
It's not 0.
It's not 0?
No. So it's 10, then 7, then 4, then 3.3, then 2.
Right, it's 10?
Yeah. 1 times 6 to the 1.
Oh yeah, okay.
10 times 6.
Oh, I didn't see the 1 there.
Yeah.
I was looking at 0.
How does it do it? Yeah.
So it goes from 10 megahertz to 1 megahertz.
It's going to go from, yeah, at the moment it's from 10 to 1, and then we set it up to do from 10, so the maximum range of the machine is 10 kilohertz to 10 megahertz, and it's going to do 20 logarithmically spaced points between 10 and 10 kilohertz.
Oh.
And then what you get is this, so that is that, and then you'll see this shift for different temperatures, and that's what the experiment is.
And that's all we're doing?
Yeah.
So we've literally just done 1 sample already?
You've done 1 temperature of 1 sample.
Alright, so we've got to repeat for 40, 50, 60, 78, 60. What was it then? 30 to 90, alright. Okay, so if you just, and then we would need to plot that, or does it already plot it?
It plots in there, but then what you should do is take these, so this gets dumped out in the file, and then you can take that, load it into whatever, Origin, Excel, MATLAB, Python, and then plot them all up.
It even works out the error for you, is it?
Yeah, it does, yeah. Whether that's right or not. Yeah, so the error comes from the least mean squares fitting of that exponential curve.
So is that the correct error then?
I think it's reasonable for you to assume that it is. It's beyond the scope of the project here.
Yeah.
Basically, no other samples look this good.
Just this one?
This is a really, no, these 4 look really good.
Oh, right.
But the other stuff like this does not look like that. It looks like shit.
So what is T1 actually telling us? What is T1?
T1 is the decay rate of these spins. So basically what's happening is that, so you stick these spins at higher energy state with a pulse, and then they lose momentum to the surroundings. They use spin momentum to the surroundings, and so they gradually decay to where their ground state is. And the constant of that decay, a bit like radioactive decay or whatever, is T1. That's it. And then T2 is the loss of spin to each other. So because they're all spinning together, they become out of phase with each other, and then because they're out of phase, they interact, and then because they interact, they slow down, and then they lose spin, and then point back up again.